I've made a few videos now showing phase measurement using an oscilloscope. In the first video I talked about using a spectrum analyzer with a phase discriminator to make phase noise measurements. So in this video what I'd like to do is show how that's done. I plan to use the HP3589A. This is a spectrum network analyzer. It's good for about 150 megahertz. I have a homemade phase discriminator that I'll use with it to make these measurements. So I want to first talk a little bit about how these measurements are done. There's a paper that HP put out several years ago by Bob Temple and Terry Decker. It's called Choosing a Phase Noise Measurement Technique. This is from the RF Microwave Measurement Symposium and Exhibition. There's a few different ways to make phase noise measurements with the spectrum analyzer. One would be direct, where we would feed our signal directly into the spectrum analyzer and try to make the measurements. The other way would be to demodulate the signal first. This is what we plan to show in this video. This is the basic setup to look at the phase noise. Here we have our source running to a power splitter, going through a 90-degree phase shift, into a mixer, into a low pass filter, into our LNA. And then this feeds out to the spectrum analyzer. In this diagram we're using the mixer as a detector, holding the two input signals 90 degree out of phase or in quadrature will produce a DC output. The output in this case would be 0 volts. Here we have our signal that we're trying to test, and we have a reference signal. So in this case we have a very low noise phase source that we're feeding in as a reference signal into our mixer. This again goes through a low pass filter. In this case we have a phase lock loop that's used to control the reference, and in this case the device under test. Depending on what you're testing, maybe or maybe not, you can't drive this with a phase lock loop. In my discriminator that I've shown before, we have an RF amplifier that has very low phase noise. It's fed into the reference input of the discriminator through a delay line. This delay line is capable of being programmed out to about 2 nanoseconds. That feeds into one side of our mixer. We also have our device that we're trying to test. The input of that goes through a low pass and then into a high pass into the other side of the mixer. The output of the mixer is then fed through a low pass filter and then into an LNA out to the spectrum analyzer. There's also a tap off of the low pass filter that goes into our DSO. We use the oscilloscope to tune the phase relationship of the two signals. The output of this also taps off into a phase lock loop. This outputs a DC signal that feeds back to our RF generator into the FM input, which is DC coupled. This locks our RF amplifier with the input. So as this input here drifts, this RF generator will automatically track the input signal. The 4360 again is only capable of going to 150 megahertz. Will again demodulate the input signal. In this case we're going to be looking at a 1.5 gigahertz clock. Again, the parts of the discriminator, there's an LNA, this is a low noise amplifier. Here's our filter, and here we have a mini circuits mixer. It's good from a gigahertz up to about 4.2 gigahertz. Here we have a high pass filter set to a gigahertz and a low pass filter set at 1.6 gigahertz. And the input of this goes up to the front jack, and this is going to be our input clock of the device we want to test. There's also a reference clock which will go to the generator, which goes to the other side of our mixer. Coming out of the LNA there's an output for the phase lock. This again goes to the FM input of our RF generator. There's an output for the spectrum analyzer and an output for the oscilloscope. Again, there's two switches on the side of the LNA. These are used to select the gain. This allows me to get a much better signal and noise ratio with the spectrum analyzer. Next, what we're going to do is test the LNA amplifier in the software by injecting a known signal into the filter. This will be from a secondary small RF amplifier. So for starts, we're just connecting the 33120 up to our 3589. So we set the generator for a 1 kilohertz wave, and what we're going to do is we're adjusting the amplitude to get a minus 20 dB signal. I really don't care about the amplitude of this. This is just basically to verify our amplifier in the software. So now we have that signal. What we're going to do is we're going to inject that into the front end of our amplifier. Now this particular LNA has a 50 ohm input impedance. So we're going to go from the LNA's output, spectrum analyzer output, and then we're going to connect that to our input of our spectrum analyzer. As we can see, there's quite a bit of gain. The output now is 5.34 dBm, and again, this is selectable. The input of this analyzer is only good to a maximum of 20 dBm. Obviously we don't want to damage it, so we'll leave it at something low. This is pretty safe. So what we want to do now is see how well the software can compensate for this and get us back. I'm running the program right now as source code, and we can see our signal here at 5.7 dB. And what we're going to do is we're going to run a sweep here and just make sure that the software is able to pick this up. So what we're doing is we're going to tell the software that our mixer has no loss. And the reason we're doing that is because there isn't a mixer in the circuit right now. So we've gone ahead and we started up the scan. As you can see here, it incrementing through our center frequency. Give you an idea how fast this thing actually is. This is with a resolution of 1.4 hertz right now. This analyzer can actually run sub 1 hertz bandwidths. So we're coming up on a kilohertz here, and what I'm expecting to see here in the noise floor is that our 1 kilohertz center frequency, we're going to see our spur. And this will be a kilohertz. And there's our spur at 5 point something. Once it reaches a megahertz, what I'm expecting to see is going to be right here. So 19.8 dB is our spur right on at 1 kilohertz. So it's out of calibration a slight amount. What I can do is go ahead and run a calibration of the LNA to take care of this offset. Next I want to show how we calibrate out the nonlinearities of the LNA. So the LNA's input, or the filter's input, is actually tied to the output of the network analyzer, and the output from the LNA ties to the input. On the software there's a button for LNA cal. We select that, and you can see here as it ramps up through the frequency. As it sweeps through the frequencies, it's measuring the gain of the amplifier, and it's going to record this into a file. You get an idea how fast this is actually taking the measurements. It's with an RBF of 1.4 hertz. We're up to 50 kilohertz so far. Test is finally completed. Took about 20 minutes or so to run. This is the flatness of the amplifier, and this is a half a dB per division. Now, I'd ran the same test several years ago, just to show you. This point here, 25.5. And 25.5. This plot is about, I don't know, maybe 5-6 years ago. It's very similar. So we hit the save cal. Software will come up and ask us for a file, and we can go ahead and write that out to disk. System uses all SMA components, and these are all torqued. Okay, with that, the system is pretty much ready to be ran. The first thing we're going to do is test the noise floor. So to test the noise floor, the output of our RF generator is driving into this mini circuits splitter. The two outputs from the splitter then drive to the two inputs of our discriminator. Again, all these signals are torqued. Go ahead and we'll set this generator up for 1.5 gigahertz. Looking at the oscilloscope here, we can see this is at 0.1 volts per division. This is looking at the offset coming out of the mixer. As I'm going to rotate the crank here, I'm changing the phase. You can see how this affects the output of the mixer. So the mixer is actually supplying a DC output at this point. As you can see with the phase trimmer, I'm able to go through a few different cycles. What we want to do is set this thing roughly to 0. This is on a 5 millivolt per division. We'll bring that right in. Now we're ready to measure our noise floor. Now we set up the discriminator to look at the noise. The next thing we need to look at is the math. So this is application note 3359. This was put out by Dallas Semiconductor. This has a date of September 23rd, 2004. This app note covers the math that's required to calculate the RMS jitter. We won't get into the math a whole lot, but it does explain a little bit of how this circuitry works. This is looking at the relationship between the RMS period and the phase noise. So they give an example here. This is typically what you're going to get from a manufacturer. There'll be different breakpoints at different frequencies. In this case, they've worked an example. They have a carrier frequency of 155.52 megahertz, and they're saying that at 10 hertz it's minus 58 dBc, 1000 hertz minus 118, at 3000 hertz 132, and 10,000 hertz 137. And they calculate out a RMS jitter of 4.042 picoseconds from a band of 10 hertz to 10 kilohertz. Here I've created a Microsoft Excel spreadsheet. See, I've set up the same breakpoints with the same dBc values. And as you can see, we calculate the same number, 4.07416. So here I've written a program in LabVIEW to do the same calculation. You see our carrier frequency at 155.52. And again, this is our calculated jitter, 4.074. Again, roughly the same breakpoints, same frequencies. This section of software is incorporated in the main program that's used to control the spectrum analyzer. With this calculation now verified, we can go ahead and calculate the noise floor. To demonstrate the phase lock loop, we have our eval board hooked up. We're just using the TCXO. One output from this eval board is going to a counter. The other output to the RF input of our discriminator. The reference input to the discriminator is going to a splitter. The source of the splitter is tied to our RF generator. The other side of the splitter goes to a second counter. The 5328 counter only has an input frequency of 1.3 gigahertz. So what I'm going to do is I've programmed up the synthesizer to output 1.278 gigahertz. This counter is actually running from the GPS receiver. This error is actually what we're getting. The generator that we're using here is the source. This also hooks up to the GPS receiver, and also this counter does. When this comes in lock, you're going to see these two counters match. The other thing we're going to see is the output of the oscilloscope is going to be quite noisy when it's unlocked, and when it goes to lock we're going to see a DC value. So let's go ahead and run that. The first thing we're going to do is program up our RF source to give us roughly the same frequency that we're running with the synthesizer. So what I'm going to do here is I'm going to unplug the FM input. And we can see here with the counter .477 hertz, 656, and now I'm going to plug this back in. You can see here 447, 477. So for me to get this out one more digit here, let's just let this thing acquire for a while. I'm going to lose the upper digit. You can see here 477 hertz, 477 hertz. Here we're looking at the monitor output with the evaluation board attached. As I change the reference clock, you can see the frequency of the output of the mixer changing. Really what we want is this to be a DC output. And now we can see the phase is locked. Again, out of phase. And here we have the lock. Just looking at my old 496 spectrum analyzer here. And this is at 200 kilohertz per division. And we can see here, this is the skirt that we're talking about. This is DC essentially. Now, right now, the output of the signal is minus 12 dB. What I'm going to do is turn this thing up. You can see the difference here. This is the actual phase noise that we're wanting to analyze. Again, running the reference is the RF generator. We can see here the difference in the noise floor. It's dropped substantially. This is looking at the output of the spectrum analyzer, again without the lock. You can see quite a bit of phase noise here. And as we bring it into lock, we can see how much it changes the phase. So this is what's left over. This is the signal that we're interested in. My 9-volt battery died, so I'm switched over to an analog power supply to drive this temporarily. I also noticed when I started playing with this board that I had to change things around just a little bit. The phase noise of this clock is actually quite a bit lower than what I showed the noise floor. So I've gone ahead and I've made a couple of changes here as far as changing the gain of the amplifier. So we should be all set now to make that measurement. A few more things I'd like to mention before we make the measurement. This is an Agilent product note that covers the 4395. It talks a little bit about the 3589A. There's not a lot of documentation available for that particular spectrum analyzer. But what I want to show you is this page here. It's talking about the effective noise bandwidth and how this equates to the resolution bandwidth. And you see here it's talking about the 3589 here in this column. If you were setting the resolution bandwidth of 1.1, the effective number is actually 1.2. The test that we're running close to 150, I think. So that has an effective bandwidth of 159. It's important to pay attention to all these details when we're actually making this measurement. Any small errors, they all add up. I'm going to launch the ADI simulator. This is for the phase lock loop that we're going to be testing. I'm just going to open up my last design file. So we run this program here. You can see I've set this up for a TCXO. It's a 10 megahertz part. We're running it at 1.5 gigahertz. These are the phase noise numbers here. So this is the total at 100 hertz, a kilohertz, 10 kilohertz, 100 kilohertz, and a megahertz. If we come down to frequency domain here, red trace is our total phase noise. You can see here it starts up at about 60 some odd, 66 dB, and it kind of swoops back up, and then it tails down to a megahertz. So when we run this test here, we expect to see something very similar to this. So let's go ahead and take the measurement, and again we just select phase, and this will start the analysis again at 100 hertz. We're up to 100 kilohertz now. Should start moving a little faster as the resolution moves out a little bit. And we're almost there. Okay. So this is our 100 hertz line here. So we're looking at 66 dB down, and notice kind of the shape here as we come up to roughly 10 kilohertz, which is roughly again what we're seeing in our graph. About 10 kilohertz we get this little hump, and then it drops down pretty quickly. At 1 kilohertz we're at roughly 85 or so dB. If we just go over to our if we go to the report here, again we were looking at 82 dB at 1K, 81 dB at 10K. So here we are here's at 10K, and you're roughly 80 dB down. And at 100K, we're at about 105 dB, and we're predicting about 102 and 131 dB in a meg. We're showing this at about 125 dB in a meg. There's a blue and a green. Every time I make a sweep, it'll save the previous run. Let's give you an idea of how repeatable the test is. Imagine a few people would like to see how low the noise floor this actually is now. So let's just go ahead and run another phase sweep. I've gone ahead and tied the RF analyzer back to the two inputs, and then set the phase. So we'll just let it sit here and collect for a little bit, and we should see the two graphs overlaid. You can see when you're making these kinds of measurements, very important that you check every little detail. Make sure you understand what it is that you're trying to measure. Can save a lot of time. Okay, we're coming up, and here's our floor. So you can see it's well below 10 dB off of this guy now. You're looking at about 146 dB down. Okay. I hope that answers all your questions about my phase discriminator. And you don't have to spend a lot of money to be able to make these kinds of measurements. We're using this analyzer again. This is only 150 megahertz analyzer, and we're testing a signal that's well up into the gigahertz range. It's really dependent on the quality of the parts that you're using. Here again, I'm just using mini circuit parts for the most, except for the LNA, which is a homemade part, and the phase trimmer, which again is an old HP part. So we can get some fairly accurate measurements with this type of equipment. Hope you enjoyed the video.